So smooth. Hey, Pamela.
Hey, how's it going, Fraser?
Good. So you tweeted out a really unnerving image just a few minutes ago.
Yeah, we have a kind of massive storm that is luckily losing some energy as it crosses the Mississippi, but there might be a bit thunderous of a soundtrack that we will curse Preston with.
Yeah, we actually heard it as we were setting up. You're like, "Did you hear that?" And I definitely heard that. So,
Yeah,
yeah.
it's now pouring rain, but we don't have hail at the moment, at least.
But I don't think. I mean, you're always threatening that a tornado could take out.
We had one hit 2 blocks away from our house.
Yeah, but it didn't take out Astronomy Cast. All I'm saying is that so far, for all your empty threats, no tornado has actually caused us to not be able to continue recording Astronomy Cast. Now, there's been a few tornado sirens that you have perhaps not you've ignored.
Yes.
But did you see my son just kind of sleep?
Yes, I did. Just blonde
in the back there. Yeah, he's sick today.
Oh.
But yeah. So hopefully we'll do fine. There'll be no
this is simply threatening to flood people who live closer to the Mississippi and be loud for us. The dog is cowering.
So a few pieces of information. One, congratulations to Astronomy Cast, the Weekly Space Hangout, and the Universe Today Guide to Space for being nominated for Parsec Awards. This takes
and 365 days of astronomy.
So we're in a 4-way battle for the things that we make with ourselves. But there's some other really good candidates in there as well. There's the Hubble. The Hubble podcast, Hubblecast, which is terrific and often wins. So we're cut up for us.
No, they haven't won yet.
Oh, they haven't?
It was Planetary Radio that won in the past.
Right.
We usually lose to one of the skeptics.
Yeah.
Star Talk's never won. It's always been it's generally been
Planetary. Yeah. Matt Kaplan and the Planetary Society team. They're so good.
Yeah.
But we won with the Guide to Space last year, and I hope I don't know. I hope I don't cannibalize the Weekly Space Hangout. Anyway, that's happening next. Well, the hand-in was today for the various samples. So, and a big thanks to the whole WSH crew for pulling together, picking all the clips that they loved the most, and getting those into the show. So,
and the Astronomy Cast Facebook group did the exact same thing.
That's awesome. Yeah. Wow. Look at this. We've been sort of getting everyone's help, and it's working out really well. Yeah. So just to remind everybody, this is a live show, and we will do our regular show, and then we will stick around for, 20 minutes, 25 minutes, and take some questions. So, and I'm going to say hi to Yov Landsman and Michael Thompson and Tony Lynch and Richard Strassel and Thomas Traniker and Richard Clark, Elad Avron, Douglas Crandall, Nancy Graziano, Guido Bibra, who I met in person just this weekend, which was on Hangout. Peter Waldman, Jill Sabarin, Sylvan Westby, Albert Braun, and Larry Beckham. So I am going to now delete all your hellos, and it's nothing personal, but I want to be able to see the questions pop in. So, if you see me kind of looking over to the side and deleting things, that's just because I'm trying to clear up the Q&A app, which, by the way, if you're watching this video, click the Astronomy Cast is interacting. Click that, and you'll come to the Q&A app, and you can ask your questions. And we'll dedicate half an hour. So hit us with your questions. Next, just to let you know, on Friday, we're not going to be doing the Weekly Space Hangout. We're going to be doing a live broadcast with the New Horizons team, Alan Stern and the Postdocs, as we call the band. And we're going to be doing that on Friday at 2:30 Eastern time. So it's going to be half an hour before we normally do the Weekly Space Hangout. And I'm going to be hosting, and we're going to be talking to the New Horizons team, sharing the latest pictures and talking about what's going to happen over the next month as New Horizons reaches Pluto. So it's going to be pretty cool. So I'll get more information out as that comes together. Whew. Okay, let's do a show.
Cool.
Do you have anything you want to mention?
We're going to be on Tuesdays with Astronomy Cast, but we should say that during the show. We also have Astro Gear the team, we have a Pluto shirt and a series shirt, but I'll say that during the show too.
Let's do that. Yeah. So just to let you know, by the way, we're going to be recording on Tuesday next week and the Tuesday the week after that, because you're traveling on both Mondays. So we'll do the shows on Tuesdays and then as we reach the end of the month. So just keep that clear. Keep that date. Save the date. All right. Let's get rolling.
Okay, I am pressing record.
Wait, no, hold on. Wait, stop.
Stopping.
I don't have my intro here handy. Hold on. Give me a second. I wrote it.
We take turns, folks.
All right. Now I'm ready.
Okay.
Yes.
Pressing record.
I'm going to press record.
Hey, Preston.
Here we go. Astronomy Cast, episode 381, Hollowing Asteroids. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. So once again, it's the summer season is upon us, and that means that your neighborhood is being threatened with all kinds of inclement weather. So if we
may have a little bit of thunder during this podcast.
Yeah, we had some thunder happen in the pre-show as we were getting prepped. We heard, I heard some thunder in the background of your recording. So leave it in, Preston. If you hear this, leave it all in.
I'm not sure how you remove thunder.
Don't remove the thunder. Yeah, exactly.
Although it looks like the storm is turning just slightly north of us, so we may get lucky.
All right. So you've got a bit of an announcement to talk about some of our astro gear.
Yes. So it is an amazingly exciting summer. Everyone is totally aware, Pluto, everyone is talking Pluto. And we have a shirt over at astrogear.spreadshirt.com that says Explore Planet Pluto Classic. It's a total parody of the Coke Classic logo, fully legal under parody law. And there's also Ceres. People keep forgetting it's the other former planet. So in the name of parodying, we parodied the pork, the other white meat logo, and made a Ceres, the other former planet. So you can show if you're Team Pluto or Team Ceres by getting yourself your own former planet t-shirts.
Awesome. Do that. Okay, great. Well, let's get on with the show.
Okay.
All right. So when we finally make the jump to fully colonizing the solar system, we're going to want to use asteroids as stepping stones. We can use them as way stations, research facilities, and even as spacecraft to further explore the solar system. So today we're going to talk about the science and science fiction of hollowing out asteroids. Now, Pamela, this is clearly one of your pet favorite ideas. You bring it up often. Yes. And it's great. And it's funny in preparing for the show, in looking back, this has been a big idea that's been shared for a lot of researchers, a lot of NASA people for decades.
Yeah. And it's one of those things that the science fiction and the science have just sort of always hung out there saying the exact same things of, hey, we can do this. We should do this. This is really cool. Look at how awesome it is. And yet we never quite get to doing it. So this is where we named this in science and science fiction, because it is near future fiction that people are working to make real right now.
Yeah, absolutely. So then let's kind of go back a bit and just sort of talk about why, I guess, what is the idea here? So you take an asteroid. What do you want to do to the poor asteroid?
Well, the asteroid doesn't care, luckily. The idea is that, nowadays you can grab yourself one of these nice carbonaceous, silica-rich asteroids that has an orbit that is very, very similar to the Earth's orbit. So it doesn't take a lot of energy to bring it to Earth if that's what you want to do, or to get to it, which you're going to have to do either way. And once you're there, you can use the material that the asteroid is made of with 3D printer to turn the asteroid into whatever you want. You can simply bore into it and hollow yourself out a hobbit hole in the side of an asteroid. Attach engines, get the thing spinning. You have a spacecraft that has built-in radiation protection because all of that nice dirt wall, it's there to protect you. Now, admittedly, these carbonaceous chondroites, these silica-rich asteroids, they're going to be kind of fragile. Maybe, we don't really know. Some of them are actually just rubble piles, but a little less than 10% of the asteroids are actually metal-rich, made of iron and nickel and platinum and all of these other metals that you can just flat out mine and turn into a spaceship. So there's a lot of potential things that you can do.
All right, so let's talk about like what it would take to actually get a mission to an asteroid and begin to do some of these things. Because, you know, I think I'm a classic oversimplifier. I know that. I know that's one of the things that I do. But we saw with the Rosetta mission, with Philae trying to land and bounce on the surface, and how it bounced on the surface of 67P, that it's actually a really difficult environment to try and work in. So what are kind of the challenges to actually interacting with an asteroid like this?
Well, the number one challenge is, how do you catch the sucker? You have an object that's moving at a bazillion kilometers per second, basically, as it happily treks around the sun. So you have to get out of the Earth's gravitational well and find an asteroid with an orbit that it's easy to sync up with. Now, once you can find that asteroid, it actually takes what's called a lower delta V, a lower change in momentum brought about by changing your velocity, to get to an asteroid than it does to get to the moon, because the moon is orbiting the Earth and it's just hard to match that.
Yeah, people don't realize that.
No, it's a pain in the butt. You
The
have to
moon is
basically
actually
go up.
difficult to get to, when in fact there are asteroids where the delta V to get to those asteroids is really slight compared to going to Mars or going to the moon.
Yeah, so you start out by finding the asteroid that has a near Earth orbit. There's a bunch of these out there, and they have neat names. One of my favorite random moments in geekdom was talking to Richard Hatch and explaining to him that a lot of the asteroids that strike the Earth's atmosphere, including the Chelyabinsk asteroid, are Apollo-class asteroids that have semi-major axes. This is the half size of their long axis, that is a little bigger than the Earth's orbital axes, and cross the Earth's orbit twice as they go around the sun. So these are asteroids that we have the potential to overlap with, which would be really bad. But they're also fairly easy to get up and close and personal with, which is really good if you're trying to catch one. So catching one of these Apollo asteroids. There's also more asteroids which have orbits a little bit bigger than ours, and all of these different things, we just need to go out and find them, which is its own challenge. But this is why we're building the Large Synoptic Survey Telescope. This is why we have the Catalina Sky Survey. Finding asteroids is something we know how to do.
Right, and there are ones.
Find it.
I think, was it asteroid Tutatis? There's a bunch that have been identified many times that they, as you said, they have an orbit that kind of interacts with the Earth's orbit, and in some cases they're pulled a little, as they approach us on their orbit, they're pulled a little forward, and then other times we catch up to them, and we sort of have this interplay with these various asteroids, and it just makes them super easy to get to. So, okay, great. We've identified a few hundred candidate asteroids that might work well for us to try and get to. So what's next?
So next you figure out, am I going to bring it back? Am I going to bring it home with me? Mom, the asteroid came home with me.
Yeah, you're going to have to feed it. You're going to have to take care of this thing.
Exactly. Then if you're not going to do that, how are you going to mine it in situ? So if you're going to try and bring it back with you, you have some options. You can paint it to change how it interacts with solar radiation so that it's either pushed more or less than it's currently pushed. You can blow things up near it so the shockwave affects the orbit. You can stick something really massive nearby so that it gets dragged gravitationally into a slightly new orbit, because you're assuming that whatever it is that you put in front of it has rockets to steer. Or you can just attach engines to it right off the bat.
You could shoot it with lasers to try and vaporize material. You could put some kind of mass driver cannon on it and shoot those, chunks of the asteroid off into space to affect its speed. So there's a lot of, and if you're really clever, you can use various flybys of smaller asteroids that you've been able to engineer and try to sort of do some gravitational slingshots with it. So many options.
Right. So figure out how you're going to move it. And then what do you want to do with it? And the thing that I love the idea of the most is turning these things into actual spacecraft where you first utilize the material that's inside of them, hollowing them out. If you've ever read Ender's Game, so I always imagine the way the insects, the buggers, hollowed out asteroids, ant style, except now do it with the same kind of massive machinery like is putting in the new tube in London, or has built channels between England and France and between different parts of Japan. Find one of these massive tunnelers, but build it in space and tunnel yourself out an asteroid and use the leftover material to build the structures you need on the surface, to build additional spacecraft, to 3D print. I mean, there's so many different things you can use that rock for given modern technology.
Oh yeah, I mean the difficulty, as we saw, as I mentioned with Rosetta, is just interacting with such a low gravity world has a whole series of complications.
Now, luckily, asteroids do have a significantly higher density than comets. So if you find an asteroid the same size as comet CG 67P, because of that difference between water and rock, you're going to have a little bit higher gravity, but that is going to be a problem. Now, we have managed to land things on asteroids before. We've settled spacecraft onto their surfaces after exploring. We're sending OSIRIS-REx out to do a sample return. But it does require very carefully matching the spin rate, very carefully not bouncing as was realized by Philae. Now, the difference, luckily, between the types of asteroids that we've landed on in the past and Chirigiri is, while I'm sure there are rubber duck-shaped asteroids out there, you can purposely choose to try and land on something that is more headed towards this extremely complex topography that was spinning around a really weird rotational axis. Trying to land on something that has a wonky spin, a really weird shape, and almost no gravity. That's 3 different marks against you. If you can at least get normal rotation axis potato, it makes life a lot easier.
Yeah, absolutely. Okay, so you've figured out how to either move the asteroid or you're going to go to it, and we've talked a bit about the kinds of technology that we would use to maybe hollow it out, use some kind of drill. Maybe we're going to use kind of more traditional explosives, the way we mine here on Earth, to try and smash pieces out. So how would you then turn that into a place that people could maybe live?
There's several different models that are out there. One of my favorites that has cropped up in several different books, it was in Seven Eves, although it wasn't asteroids, it was chunks of the moon with Seven Eves. It's in Kim Stanley. Seven Eves is by Neil Stephenson. It's in 2312 by Kim Stanley Robinson. The idea is you completely hollow out the object and set it spinning to create artificial gravity, and then use this to create a pocket environment. And the amazing idea put forward in 2312 is, imagine as we're trying to protect the various ecological systems here on the Earth as climate change is, well, moving where the ecological systems are comfortable. The thermal gradient of the oceans is changing. Our deserts are shifting. This is causing things like polar bears and penguins to really struggle. Now imagine that you can recreate each of these different ecological systems inside one of these asteroids to not just create a Noah's Ark of seeds and genetics, but a Noah's Ark where we're actually sending the animals not 2 by 2, but probably genetically diverse multiple of at least 8 or 10 at a time, and well, setting them loose in these different ecological niche asteroids.
And so that this idea that you spin them, you hollow them out, you spin them, you get artificial gravity on the, I guess, on the edge and the inside rim of the whole asteroid.
Yeah.
How big of an asteroid would you need that you could actually set it spinning and use that gravity?
Well, it's a matter of how fast you want to set it spinning. One of the problems with a normal donut spacecraft that we think about is you build multiple stories and it's a thin ring, so you want to set up those multiple stories. And if it has too small a radius, you very quickly have radical gravitational changes over very short distances. If you had something that was just 100 meters or so, but single storied on the inside, you'd be fine.
Right.
It's that single story that
it's
makes
the single story.
Difference.
Right.
Yeah.
I've read some descriptions of this, right? That as you tried to climb up a ladder in one of these spinning things, your gravity would change rung by rung as you went up the ladder. You start at, say, 1 Earth gravity, and as you got to the top of the ladder, you'd be at 0 gravity again. It'd be pretty weird to kind of move between those situations.
And this is another one of those things that comes up over and over in fiction books, because if you sit down, you do quick calculations, it very quickly becomes apparent that, yeah, the rung by rung is all it takes to suddenly find yourself in 0 gravity instead of full gravity. One of the ideas that's put forth, and I'm trying to find the title, I'm switching between different screens on my computer, unfortunately. One of the ideas that comes up in a variety of different fictions is you end up actually, unfortunately, having a caste system where it's the wealthy who live at 1G. It's the wealthy who get all of the physical and psychological benefits of having sufficient gravity to make things easy to deal with. And as you become more and more impoverished, you end up getting essentially thrown away to the lower gravity areas where you physically suffer. This is one of those problems if you think about doing a mined out termite style, anthill style asteroid, setting that kind of asteroid instead of one that's fully hollowed. Rotating means that you still have the center of the asteroid that has no gravity and is just spinning, and that's not useful for anybody.
So what would you do with the material that you pull out of the asteroid?
It depends on what it is that you're pulling out. If you're dealing with a metallic asteroid, well, that's clearly the type of material that you use to build additional spacecraft, additional machinery, to build your rocket engines, to build your control systems, the things that you mount on the outside of asteroid that turn it into that fully steerable spacecraft. For three have been put forward. The idea of you just basically pitch it out the side has been put forward. Then there's also the question of water. People worry about, do I need to harvest water from perhaps Jupiter's moons and bring that water back to the planet Earth, or to the asteroids that you're harvesting? But what we're learning today is some of these asteroids are actually the sources of, well, probably the water here on Earth. And so we probably need to be mining asteroids for water. So in a perfect world, you find that thus far not documented asteroid that is a healthy mix of silica and metals and water, where you 3D print whatever you need from the silica, you mine out the metals and use it to build your engine parts, and you have the water you need to start building that environment. That's the one problem with the hollow asteroid idea, is you still have to get the gases to fill the asteroid from somewhere.
Right. And so you could imagine that maybe they might be ice mining as they try to move through it's not just going to be rock, it might be rock mixed with ice. And so you can imagine these kind of tunnels of rock and ice as they move through the asteroid. So what are the advantages of, I guess, of having this kind of a place? I mean, you talked about, let's keep it as a lifeboat to help preserve some of our genetic material, so that if something ever happens to Earth, we've got another place where this stuff exists. But I guess, what is really the advantage of just having manufacturing facilities and stuff in orbit already? I mean, there's tons of benefits to that, right?
One of the big benefits is you're out of Earth's gravity. Once you're out of Earth's gravity, it becomes much less energy intense to figure out, okay, how do I take off for Jupiter? How do I head into the inner solar system? And if you can build all of your high mass, difficult to move objects in space already, you don't have to lift them out of Earth's gravity well. This is a huge savings in fuel. So you start from hey, I'm saving energy by doing this in space. And this follows up with you're not depleting the Earth of resources. And in fact, you're revealing resources that you can potentially bring back to Earth. This is, again, something that comes up in numerous sci-fi stories. The idea that, and it's also part of what Planetary Resources is looking to do, we have only limited resources on the planet Earth. At a certain point, we are going to run out of certain rare metals. We're going to run out of helium-3. As we run out of these things, outer space is pretty much the only place we have to go, refuel ourselves.
Right. So it's almost like the value of that material in space is so high that as you hollow out the asteroid, you can sell the stuff that you're pulling out. The water ice will be super useful for rocket fuel, for breathing, for making food. The silica, you can use that for building materials. The metals, you can use those for, as you said, rocket parts, or you can sell them to Earth and you can send back huge chunks of palladium and platinum and have those safely come back into orbit, re-enter the Earth's atmosphere and make them available to people on Earth. And that could fund the whole process. So yeah, there's definitely some money to be made to pay for the exploration. One thing I'd like to talk about then is sort of the big sci-fi dream, is that you could use this as a spacecraft, both to explore the solar system, but maybe even to go to other stars.
And one of my favorite books, and it is one that will utterly wreck you. Like, I was on the London Underground sniffling and blinking back tears. It will wreck you. Have happy, fluffy goodness and light young adult fiction waiting to read afterwards. Mary Norris Russell's book, The Sparrow, starts from the idea that we detect signals, music from an alien, we assume alien civilization. And while most of the people of Earth are debating, what do we do? And the governments are trying to figure out if they have money to do anything. This is in a future where we are mining asteroids. And the Catholic Church has enough money to, while no one else is looking, dispatch a asteroid turned into a spacecraft on a relativistic journey toward this alien civilization with 1G acceleration the entire way, where you're accelerating up to the halfway point and decelerating down from there. And this is kind of that core idea of, in the future, when we want to get from one place to another, accelerate the entire time, have the gravity that you want. And asteroids are just there waiting to be used, waiting to be mined, and we don't have to solve the radiation protection problem with them. That's the thing I really appreciate about them.
And the micrometeorite impact problem.
Yeah, they're used to that.
Yeah, but it's huge. I mean, you look at the solar array on the International Space Station, and there are holes from either space debris or micrometeorites that are pelting this. And so any one of those could just smash a hole right through your spacecraft in an instant, moving at 27,000 kilometers per hour, and you would just be destroyed. So having 100 meters of rock around you would be really helpful for those kinds of impacts. You're not
going to have a thickness of 100 meters around you, but having sufficient thickness of rock around you. Think adobe walls, but reinforced.
Yeah, would be great.
Yeah, it's in, and the book series that I was forgetting the name of is James S.A. Corey's Leviathan Wakes series. Throughout this series, which is classic space opera with a twist of zombie for flavor, it has throughout it the idea that humanity has expanded past its ability to remain confined to the planet Earth. There's just too many humans. And so we spread out across the solar system, including hollowing out Ganymede, Vesta, these other worlds throughout our solar system. And there's the amazing notion that you're walking along the halls on Ganymede and you can't touch the walls because you'll freeze your skin. And that's just a really neat thing to think about, that we do need to worry about those things as we start hollowing these worlds.
So, I mean, this is just mad science fiction, and it makes science, but it makes my mad speculation just look like stone cold reality. So what work is being done right now to sort of move us in this direction? You mentioned briefly what planetary resources.
Planetary resources, I think, are really the leaders in putting their money where their mouth is. They have kickstarted early test technology. They have a multi-year plan. They have the company. This is something they are working to do, and they are working to discover and map out the asteroids. They're really the people to watch, but they're not the only people in the process of doing this. There's an international organization called Project Icarus, Project Hyperion, that is done by a group called Icarus. Different nations are looking at this. I've heard graduate students present the maths in hopes of someday living the reality.
Yeah, and NASA is actually right now figuring out a mission to go to an asteroid, pick up a big boulder, and bring that back and put into orbit around the moon, and start to manipulate these space rocks, which is sort of a really big first step for us to be able to go down the road of being able to reach out to them, land on them, mine them, live on them, be a true spacefaring civilization.
And this is clearly one of those places where, everyone wants to go back to the moon. And I think the commercial folks are going to be the ones to do that for us. Lots of people want to go to Mars. I think it's going to be Elon Musk that does it for us. The asteroids are these kind of not so photogenic potato and avocado and dog bone shaped objects that lurk out, just about everywhere. And they don't get the hype they deserve as really being the place with the resources that we're going to need going into the future. And it's awesome to see that as much as people try and redirect all the resources back to Moon or Mars, the asteroids and their low delta V requirements continue to be one of the places we're looking to go.
Yeah. Great. Well, this was a nice palate cleanser from from all of the science physics experiments series that we had done. So we've got a few more of these as we reach our summer hiatus. So, well, thanks, Pamela.
Thank you. And save. And now it's all sunny and light outside. Apparently, recording astronomy cast clears the bad weather.
Yay. Right. Saved. So go and get your questions in. Use the Q&A app. We got time for questions. We're ready. If you haven't already.
I kept seeing the questions coming in while we were talking.
I might have incorporated a few in the show, but yeah, absolutely. So one big piece of news is Philae woke up.
It's alive. It's alive.
Yeah.
And I want to give a shout out to Thomas Tranneker, who has been single-handed Vesta like a champ over at CosmoQuest. We are doing our Summer of Science, and you are all invited to help us map out Mercury, Mars, Vesta, the Moon. We have a blog post up that actually lists some of my favorite audiobooks that are scientifically paired to these different worlds. So grab yourself some summer reading, stick it in your ears, and map other worlds.
Fantastic. Okay, so I'm doing my upload. So let's go. So first, Larry Beckham says, I think Ceres is a better goal for humans than Mars after the moon, especially if Dawn confirms water. Low gravity for landing and return, and Ceres could be the primary refueling station for the solar system. What do you think? Love it.
Yeah, I'm pulling up orbits.
Yeah. So it's going to have a delta V, I'm trying to think, halfway, not as much as Mars. So I'm sure somewhere there's a delta V calculation for Ceres, but I think you're exactly right that there should be water available. We see these mysterious white spots on the surface of Ceres. Those are most likely ice deposits that are just like sitting there on the surface of Ceres. So I totally agree. And it's big enough that we could get, you dig a hole under the surface of Ceres and you get some gravity in there as well.
It's enough further away than Mars that it starts to get, may not be as good an idea. What's actually probably the best idea, it's not Ceres, but actually one of Mars' moons. So heading to Mars' highest moon, Phobos is the one that gets looked at the most. It's easy to get to, low gravity, nice, easy to aim for gravitational well. So you can get pulled towards Mars, but you don't have to sink all the way to the bottom of the energy well.
Yeah.
So that's.
But actually, one of the videos that we shot our next round of Guide to Space videos, and one of the ones that we did this week was terraforming the moon, which actually is a appreciated place that we could terraform. The problem is that we would just need to smash it with a whole bunch of comets to bring in some water ice to thicken to give the moon an atmosphere. Now it is going to lose its atmosphere over thousands of years, but as long as you had a source of continually replenishing the atmosphere. So a place like Ceres, maybe, which has a built-in source of water ice, you could set up factories and actually manufacture an atmosphere on Ceres and just pump that stuff out into the around Ceres, and it would lose its atmosphere over thousands of years, but it would be a place that you could actually make habitable.
I can't imagine that it is easier to smash that much stuff into Ceres than it is to build domes and fill them.
Well, it's not that you smash it, it's that it's already in Ceres. Ceres has already got the water and ice that you need. The moon is bone dry, but Ceres actually has lots of water ice on it.
It wouldn't have enough to create an atmosphere, though.
It could be like half water ice, right? We don't know how.
Even if it is, that wouldn't be enough.
Well, did you I think the math was to make an atmosphere on the moon would be 100 Halley's comets. So, and they're what, 10 kilometers across. So anyway,
Yeah.
I thought it was a pretty spiffy idea. So that's what I'm just saying. Take series, pump out all the water, and make an atmosphere, and you got another world.
In a dome.
Although
I'm adding a dome.
All right, you can have a dome, or you mine it out as we described.
Yes.
Okay, Nancy Graziano asks, is it possible for an asteroid to be radioactive, and could it be mined not just for fuel? Does plutonium-238 occur naturally, and could it be mined for RTGs by spacecraft equipped to use them? Is there, could we find processed high-quality plutonium? I don't think so.
No, we're not going to find processed high quality. I have no clue which isotopes are naturally occurring. I'm kind of bad at remembering things like that. But yeah, 238 looks like it is synthesized from uranium-238. There is entirely the possibility of finding, in not that different proportion to what we find here on Earth, radioactive materials, except they're going to be scattered amongst all the different asteroids. So imagine taking the Earth, making it way smaller, and chunking it into a bazillion little bits and scattering it, well, around an orbit bigger than Mars' orbit, and then throwing some of them into the inner and outer solar system for fun. And that's what we're looking at. So just as we have some uranium here on Earth, there's going to be some uranium in the asteroids. In general, there is a ratio set for how the different isotopes exist that is defined by how many supernova went into feeding the formation of our solar system. Most of the rocky worlds are made up of varying amounts of these, but the materials, when they do appear, often appear where the rare things stay rare and the common things stay common.
Right. So there could very well be chunks of uranium on those planets, and you just set up some centrifuges and get spinning and turn them into high quality plutonium. Like, that's, of all the magical things that we're going to find in asteroids, we're going to find uranium. There could very well be, there are asteroids that are going to have more platinum on them than everything we have on Earth. And platinum is just a heavy metal, right? And uranium is an even heavier metal. So
and the issue is going to be just which rock do you grab that has which elements in it. It's going to take us a while with the rare ones to figure things like that out.
Yeah, and that's the kind of thing that the upcoming science missions are definitely going to be checking out. Like, I'm sure when OSIRIS-REx brings back specimens from its asteroid, they're going to be seeing how much uranium is in here, how much metal is in there, and then we'll get a much better sense of what's available.
It won't be a big enough sample to do all of that.
They'll determine what that rock is made out of, and that will give them a sense of what kinds of elements are probably located in an asteroid. So, James Tummins asks, are there any treaties that would enhance or inhibit commercial use of space resources like asteroids? I understand there may be a treaty restricting mining.
I think we have treaties for the moon. I don't know about for asteroids. I just don't know. I can Google. You can Google.
Yeah. So I think the International Space Treaty prohibits the use of claiming any place for a country. So you can't, for example, colonize the moon. Like Canada, we can't colonize the moon and then call it a piece of Canada. But there are parts in it, I think, that do allow people to use resources outside of space for other purposes.
Yeah, there's a whole lot of articles out there that have titles, "Does asteroid mining violate space law?"
So this is one of those things where possession is 9/10 of the law, right? And so if you get your mining ship onto the asteroid and you start mining, and people are like, you can't do that, and you just say, you come and stop me. So there you go. Keith Mukai asks a great question, which is, how efficient is it mass-wise to use an asteroid for shielding versus man-made materials? Could a free lunch end up costing us more energy in the long run as we try to push that mass around in space?
No, the real issue is you need to have really thick walls in order to protect yourself from radiation. And one of the big reasons that we're not on our way to Mars right now is we don't know how to protect ourselves from radiation with realistic built spacecraft. So hollowing an asteroid really is easier since we don't have the technology.
But the energy required to, for example, accelerate an asteroid is pretty high. I mean, I think that, but as you said, you paint one side of it and you start to get a thrust if you're willing to be patient. So it always comes down to how quickly do you want to get where you're going. If you're willing to wait a long time, then you don't need a very big change in your propulsion. I think the other part is that sometimes you're going to be building a spacecraft out of material from the asteroid to take you quickly from place to place, or probes and things like that. Other times you're just going to use these asteroids as a place that is safe, that you can get to, and not worry too much about trying to move it anywhere.
And one of the ideas that's really cool that Kim Stanley Robinson has in 2314 is you purposely shift the orbits of the asteroids so that they have intercepting asteroids that allows you to basically work your way between worlds by jumping between asteroids with convenient orbits.
Yeah, absolutely.
Imagine it is all. Go ahead.
Yeah. Oh, just to say that there's these great free return trajectories you can take through the whole solar system that uses almost no energy. You can just drift from place to place. And so you could imagine we get the asteroids into these drifting highways, and they just move through the solar system following this path. And so there will always be an asteroid relatively nearby that you can go to for supplies as we get enough of these moving into this trajectory. So it's pretty amazing. So Elad Avron asks, so speaking of spinning, why in science fiction do they always have one section of the spacecraft rotating instead of just rotating the entire spaceship? They're in space, there's no aerodynamics, and momentum would keep it spinning, right?
So normally what you see is there's a ring around a central axis and the entire thing is rotating, but you don't notice the center part rotating so much. And the reason they have the one ring is it's hard to build big things like rings. You can't exactly assemble them on Earth. You have to launch them in pieces, which is a pain. What you actually kind of want is counter-rotating rings so that you can not have to worry about gyroscopic forces making it hard to manipulate or maneuver your spacecraft. You are gyroscopically stabilized with that single rotation.
Right, like a helicopter with two blades.
Yeah.
But the other sort of possibility, right, is this idea that you have a static central area that isn't rotating, and then you have the part that's around that's rotating, and that creates a place almost like where you would dock to, right? So you don't have to.
And you see that in Ender's Game. You see that in Babylon 5.
Yeah, exactly. And Babylon 5 is a great example where it had the central part of the ship, and then it had the rotating areas where the humans who hadn't figured out how to make artificial gravity yet had to live, which was just great. Finally, somebody had dealt with the fact that there's no such thing as artificial gravity. So everything, but I think you're exactly right? That you're going to have counter-rotate. So you probably have some kind of central area, counter-rotating rings that stop you from getting that torque. And so then the central area is the zero gravity place where people dock and they float through, and then they get onto one of those ladders and lower themselves down into higher and higher gravity. Or they get on the elevator. It'd be the weirdest elevator, wouldn't it?
Yeah.
Right? You'd be on an elevator.
Probably be prone to breaking down.
Yeah, you'd be on this elevator, and as you went further, you would start to feel, I guess, bump against the wall, and then you would start to get more and more gravity until eventually you reach the bottom of the shaft and you were in full gravity. It'd be so weird.
one of the things that comes up with Star Trek Enterprise, which is one of the few times I did not find myself shouting at the television, is they have the notion that there's that place where the gravity flips. So why you would have that when you have artificial gravity, I don't know. But if you have a spinning spacecraft, you will have that point in the center where the gravity flips and the floor becomes the ceiling. So be careful as you travel.
Ian McLaughlin asks, okay, so climb the ladder towards the center of the hollowed asteroid. Now weightless, take away the ladder. How do I get back down?
You're stuck.
You're stuck. You don't. And in fact, well,
you blow.
You blow, but the thing is that when you think about it, right, the whole mass of the asteroid, including the air inside, is going to be rotating. And so if you move to one of the edges, I guess you're going to start bumping up against the air, and that's going to act like a drag, and that will start to sort of gently drift you towards the edge of the asteroid. And hopefully you have sped up and started to accelerate an equivalent amount before the houses come through and smash you. But I wonder, is it backwards? Would you tend to drift out, or would you tend to drift in, right? If the whole thing is spinning, and well, it's not about gravity, right? Because let's imagine the whole thing is essentially zero gravity, and the whole thing is spinning, and the air mass is spinning inside of it. The air is also going to suffer the centripetal force, and it's going to move out to the edges of the asteroid as well. So you have a place that has no air in the middle.
The death spot.
The death spot, yeah. And then I'm just trying to think what would happen to you. Would you tend to drift?
Once you would tend to drift towards the edge once you left that unstable, it's an unstable equilibrium in the very center.
Yeah, this is really interesting. I don't know what would happen to you. I'm just trying to think of the physics. You would get
drifted towards the outside once you left the unstable equilibrium in the center.
And then you would hit more. You get caught more and more with the drag of the atmosphere, and then that would push you more and more to the edge. And the question is, really, how quickly are you going to re-enter the atmosphere and smash into the side of the wall of the rotating asteroid? So anyway. That part we haven't done the math on. Let's see, what else have we got here? Cecil Morgan notes Star Trek original series for The World is Hollow and I Have Touched the Sky.
Cool.
Let's see. What else have we got? Ryan Schmitz asks, if you brought the asteroid home and hollowed it out, would the loss of mass require periodic velocity boost to prevent it from crashing into the gravitational host like we have to do with the ISS?
The reason we have to keep boosting the ISS is actually because of atmospheric drag. The mass of the Earth is so large compared to the mass of satellites of any asteroid you're going to bring back that you can disregard the mass part for the asteroid and just use the mass of the Earth in calculating your orbital velocity. So as long as you're in a high enough orbit to be avoiding atmospheric drag, however much mass you remove from the asteroid, it's negligible compared to Earth.
Right. As you remove the mass from the asteroid, it's going to cause, I guess, a little bit of a Newton's third law reaction, depending on how hard you pull it away from the asteroid, right?
But just so I think the question is, with gravity, you have gravitational force is gmm over r squared, so you have to consider both the mass of the object. But when you're looking at the needed velocity to stay in orbit around something, you generally need to use the sum of those two masses. But where the mass of the Earth is so large, you can ignore that second mass in calculating the velocity to stay in orbit. So his question, I think, was, if you change the mass, does that change your needed orbital velocity? No.
No, it doesn't.
Now, if you remove the mass symmetrically in all directions, you're good. Now, the reality is you're probably going to asymmetrically remove the mass, have conservation of momentum issues, but that's all minor thruster variations.
Added synergy notes, and I have no idea what he's talking about. Would static vapor air retention keep air in hollow asteroids? Charge the hollow asteroid with static electricity and let out water vapor at a high altitude. H2O is a dipole, pulls the water vapor down and keeps the air in.
No idea.
No idea. But I like the sound of that. Richard Clark asks, could you core out an asteroid, fill the core with water, seal it, and then heat the asteroid up to semi-molten and wait for the heat transfer to boil the water and inflate it? Presto, you have a hollow space with an atmosphere. Would this work?
That seems like a whole lot of energy that I don't know where you're going to get it. So yeah, but too much energy, not worth it.
Right.
The thing is that if you inject water into a hollow vacuum, it's going to boil automatically. And since most of these aren't pure metal, if you make them molten, all they're going to do is break. So what you're really better off doing is hollowing that sucker out. You have a vacuum. As you add in liquid, the liquid goes straight to gas, fills it in.
Let's see. So Thomas Traniker notes, one, he's just wrapped up 1,000 crater asteroid mapping bender, but also the biggest problem with an asteroid is that of power, collection, storage, and infrastructure. No power, no spacecraft. Yeah, absolutely. Yeah. So get close to the sun where there's lots and lots of power to make your solar panels work.
Or let's start producing polonium for RTGs again.
Absolutely. Okay, great. Well, I think we've run out of time, and actually there are some great questions still waiting, and I apologize to everybody, but I think we need to keep rolling. So hey, big thanks, Pamela, for this show, and this was your topic. I know this was one of your favorites, so I'm really glad we got a chance to do it. Thanks to everyone watching us this week. We always appreciate your support, your commentary, and it means a lot to us to see the community talking while we're doing the show. It feels like we're hanging out with a bunch of friends while we do this, so it just feels great. All right, so remember, Friday 2:30 is going to be Eastern time, is going to be the special show about New Horizons. So no weekly Space Hangout on Friday. Instead, half an hour earlier will be a special on New Horizons with the New Horizons science team and folks from NASA. So it's going to be hopefully it's going to be a good show. I am under a lot of pressure to moderate with a lot of important people.
And less scary, we have the Google Lunar X Prize team hangout tomorrow at 10 a.m. Pacific. We're going to have another set of great explorers getting ready to go on their way to the moon, coming on to tell us their plans.
That sounds great. All right. Well, thanks, everyone. We'll see you all, remember, next Tuesday. See you later.
Bye-bye.